Hello everyone, my name is Osama Makansi and I'm happy to be here presenting our work on exposing the challenging long tail and future prediction of traffic actors. This is a joint work with Ozgun Cicic, Yasin Manakshi and Thomas Proft from the University of Freiburg, Germany. This project was funded by the KA Delta Learning Project and the Excellence Strategy CIPSS. There are two main streams for the future prediction task. The egocentric view on the left, where the camera is mounted on the car, and the prediction in the format of bounding boxes, and the bird eye view on the right, where the scene is static and objects are only considered as 2D points. Our approach in this paper is applied for both streams. To start motivating our approach, let's have a look at the histogram plot for the ETH-UCY benchmark. Here the pins of the histogram represent the errors of the prediction obtained when running the Kalman filter. We observe that most scenarios are well solved by the Kalman filter, the blue part, while the challenging scenarios, the red part, are less frequent, much harder to solve, and indeed the most relevant ones for decision making. Additionally, we show an easy scenario where the target pedestrian, red box, continue on its way, and the challenging scenario where the model has to reason about interaction with other pedestrians, black boxes, to avoid collision and turn right. In this paper, we address mainly the challenging scenarios of the task. To get more insights, we plot the feature space and color the scenarios according to their difficulties based on the Kalman filter errors. The brighter the color, the more challenging the scenario. Doing so, we observe that challenging scenarios are scattered over the feature space and dominated by their surrounding easy scenarios. Here we zoom in and show a few scenarios. In the challenging scenario 1 on the bottom left part, the target pedestrian red will turn left in the future to follow other pedestrians. However, the scenario is placed in the feature space next to many other easy scenarios, for example 2 and 3, where the simple extrapolation solution, blue, is the right solution. Alternatively, we argue that scenario 1 should be placed in proximity to other challenging scenarios, for example 4 on the top, where they can share relevant features. This is exactly the main idea of our paper. In particular, we propose to reshape the feature space such that we push the challenging scenarios closer. In other words, this can be seen as clustering the feature space based on the difficulty of the scenario. The main benefit is twofold. First, challenging scenarios are not minority anymore within their zone, thus cannot be ignored by the network. Second, by pushing them closer, they can share relevant features, which yield better prediction, as can be seen by the blue trajectory of scenario 1. To implement our idea, we form a joint optimization between any future prediction loss, for example EWTA, and the contrastive loss. Note that our approach is agnostic to the network architecture and is simple to adapt into existing frameworks. In this paper, we experiment with two state-of-the-art frameworks, Trajectron++ on the top and FLN-RPN on the bottom. Note that only the red part is added to these frameworks. Here we show the average errors over all scenarios and over the top 1 to 3% of the most challenging scenarios. We observe that optimizing jointly with the contrastive loss yields significant improvements on the challenging scenarios while maintaining the performance on all cases. We also compare to recent methods addressing long-tail classification, for example LDAM and BAGS. Our approach based on the contrastive learning outperforms all of them by a large margin. On the new scenes dataset, our approach yields the lowest error across all metrics and all difficulties. Similar conclusion can be drawn for the egocentric view. Moreover, our results on Waymo are a form of zero-shot generalization since we didn't retrain on its training split. Qualitatively, we show a few challenging scenarios where we plot the ground truth trajectory, red solid line, the prediction of the baseline in cyan, and ours in blue. Notably, our prediction avoids the collision with other moving pedestrians, contrary to the baseline. Here, our prediction in blue reasons correctly about the semantic map of the scene, thus approximates well the ground truth. For the egocentric view, we show the past frame in top, the future frame in bottom. Here, a running child is crossing the street. Our bounding box prediction in blue is more reasonable and closer to the ground truth than the baseline in cyan. Thanks for your attention.